So my name is Ben Corte, and today I'm going to be talking about some modeling work that I've been doing in relation to an effect called temporal averaging. So to first give a brief overview of my research, I study timing primarily at two different levels. The first is at the neural level, using things like electrophysiology. So I just train rats up on some kind of timing task, and while they're performing that task, I record from neurons in the brain, and I look to see how the activity of those neurons relates to performance. And from that, I try to construct simple models that suggest how timing behavior might emerge from neural circuits. So that's on the one hand, the neural work, but on the other hand, I do really enjoy studying timing from a purely cognitive or behavioral perspective. So I like working with models like SET, BET, LET, packet theory, that kind of thing. But what I really enjoy in this domain is thinking about how the timing system works in realistic contexts and taking an evolutionary perspective in particular. So how does the timing system keep us and other organisms alive? Because the data we've collected thus far suggests that the timing system has been relatively preserved across species. So during that time, it's been exposed to all kinds of environmental pressures and regularities. And I like to design behavioral experiments that'll test whether or not mechanisms have become built into the timing system to adapt to those pressures. And I'm going to unpack that a bit in this talk with one example, and hopefully it'll show that while these sound like two different worlds, the behavioral and the behavioral work that I do on the one hand always winds up constraining the types of neural models that I can propose. So to first give an overview of the tasks that I use to study timing, I primarily use the peak interval procedure, which I'm sure many of you are familiar with. So I'm still going to give a brief review here, though, just in case. So in my case, it's fairly simple. I just take a rat and I put it into an operant chamber where it has something it can respond on, like a lever that it can press. And occasionally I present that rat with some cue. So for example, a tone might come on, and I train the rat that whenever this cue is presented, is to try to press that lever after it thinks a certain amount of time has passed. So you can take 10 seconds, for example. The tone comes on, the animal presumably estimates time as it's passing. Whenever it thinks 10 seconds is up, it'll indicate that by pressing that lever. And during some trials, the first response that occurs after that interval has passed will result in the word delivery. And the trial will end, so the cue will turn off, and the next trial will start after some period of time. But during other trials, probe trials, which we really focus on, we just leave the cue on for a really long time to see when the rats respond the most. And this data is important because on individual probe trials, what we see is the rats emit a burst of responses that tends to cluster around the interval being timed. So 10 seconds here. And across trials, there's some variability in when that burst occurs, to where if we average across trials to look at mean response rate as a function of time, we start to see normal-ish looking distributions start to form. So on the x-axis here is time relative to that cue turning on, tone. At time 0 is where it's popping it up. And on the y-axis are those lever press rates averaged across trials. So at time 0, the tone comes on, those response rates are low, but they start to increase up to a peak that typically falls around the entrained time. And then after that point, they descend again. And we can fit these distributions with something like a Gaussian to get an estimate of that peak time. And we usually do find that they fall around the train duration. So all this is indicating is that when we're presenting this tone, the animal is using the information it's gotten across training to guide its decision making. And so long as this makes sense, the only added complexity I have in my task is that in addition to having trials where I'm presenting this tone that tells the animal to respond after 10 seconds, I have other trials where I present a separate cue. A tone comes on, a light comes on, and that tells the animal to respond after 30 seconds. So when I present that light, I still see this peak-shaped distribution form, but now the peak time is falling over this cue's interval, so 30 here. All right, so this task has been very dominant in the field, particularly in the rodent literature, and as a result of its use, when people are proposing neural models of timing, they're often, when they publish that first paper where they lay out the theory, they dedicate a lot of effort to explaining how their theory accounts for performance during either this task specifically or something quite like it, where an observer tries to time a motor response around some interval of time. So given its dominance, it's worth asking the question of whether or not this task truly captures how timing works in realistic contexts. Because that's what we want. We want both behavioral and neural models that explain how the timing system works in daily life, and not just during this specific task. And if we, kind of just analyze the diagrams that I'm using to explain the task, we can see that there's a lot of artificiality here. So you have a rat pressing a lever to earn reward, which you'll never see in the real world. You have this arbitrary cue, a tone telling the animal to respond after a completely arbitrary interval of time has passed. So those critiques are valid, but I would argue that we're obviously going to need some degree of artificiality to study timing in a controlled way. But one concern that I have, and many others have, is that during this task, there's a profound lack of ambiguity that doesn't reflect how things work in the real world. And to kind of clarify this, during any given trial in this task, everything the rat needs to know to guide its decision-making is informed by a single source of information. So in other words, or for example, when the tone comes on, the animal has all the info it needs, respond after 10 seconds. If the light comes on, the animal knows to respond after 30. It's very black and white and kind of reflexive, and decision-making in more realistic contexts is often more based on more ambiguous information. And we can use myself as an example of that. So I was unfortunately recently in the situation of having to try and find a postdoc position for after I graduate. So fortunately, this is resolved by now, but I had to make this really important decision. And to inform it, I sought out multiple sources of information. I consulted with my mentors frequently, so John Freeman and Crystal Parker. I talked with folks in my cohort who are in the same boat as me for advice, and there's no shortage of people talking about this on the internet. So we have things like Twitter and Reddit and the internet more broadly defined. And the picture I'm trying to paint here is that I have this single decision to make, and I'm seeking out multiple sources of information. And importantly, nobody's telling me exactly what I should do. You know, do this, Ben, and don't think anymore. Everybody's saying kind of ambiguous, incomplete information, and they're often saying conflicting things. So I had to, integrate all this information to make, an informed decision. And this ambiguity pervades decision-making in our daily life. And in my opinion, it's profoundly lacking during this task. So one thing I want to clarify up front is I'm not saying I think all the data we've collected with this task is worthless. It's clearly informative. But I do think it's important to start asking the question of whether or not we can modify this task in any way to get it to more accurately capture or tap into this ambiguity that we see in the environment. And there are multiple ways to do this, but the way I've been setting up is to run what's called a temporal averaging experiment. So to run this type of experiment, you do everything that I've explained thus far. You have trials where you present one cue, let's say a tone that tells the animal to respond after 10 seconds, and another cue, a light that tells the animal to respond after 30 seconds. But once you see nice behavior start to form like this, you start to insert a few trials where you present both cues together at the same time. And importantly, you never give the rats any kind of instruction about when they should respond during these trials. You kind of the whole point is to see how the rat's going to react to being put all of a sudden in this ambiguous situation, where it has two sources of information to juggle, and they're both saying different things. So the tone says respond after 10 seconds, the light says respond after 30. What's the rat going to do? Is it going to pick one cue and time that or the other? Or is it going to try and do both things? So respond at 10 seconds, respond at 30 seconds. Those are plausible, ideas, but what the rats do during these trials is actually much stranger than that. And I'll plot that here in black. So during these trials, we're presenting this compound cue. We still see a peak-shaped distribution that's unimodal emerge, but now the peak time falls in between the two entrained durations. And we call this temporal averaging. And the idea is that during these trials, we're presenting both cues at the same time. The rats don't try to pick one piece of information over the other or try to do both things. They integrate the information associated with both cues into an average, and they time that average interval in an otherwise normal manner. So this behavioral effect is really interesting in its own right, in my opinion, but it also is heavily informative to our neural models of timing. And somebody who's talked about this a lot is my former mentor, Matthew Mattel, who during his PhD proposed what was at least the initial form of the striatal-beat frequency model of timing. And ironically, he's also the first person to start studying temporal averaging with this task in any kind of a thorough way. And I say it's ironic because this averaging behavior, this integrative behavior, is very difficult to get out of this model. I unfortunately don't have much time to go into it, but it's suffice to say, nobody has come up with a convincing explanation for how temporal averaging can emerge from the model as of yet. So fortunately, Matt got some funding to study the neural mechanisms of temporal averaging, and around that time, I joined the lab. And while Matt's model had trouble accounting for this effect, there was another model that was recently proposed by Patrick Simon and also many others. So people like Fouad Balki and Francois Levet, that, while this theory couldn't outright account for averaging, it seemed much more likely that there would be a way to get it to work by modifying it. And I worked on this problem for a year or two, and we often worked in collaboration. It was always very frustrating because it always seemed like we were an inch away from an answer or some kind of aha moment. And then, I ended up graduating and moving on, and it kind of got sidelined. But fortunately, during the pandemic, I had plenty of time to sit around and think. So I started tweaking with an idea that I think does seem to work. And that's what I'll be going over here. So I'm going to talk about Pat's model, what it is, why in its present form it can't account for averaging, but how a simple modification can get it to work, or seems to. So to state from the outset, this isn't a model of a network model of timing. It doesn't try to explain how different areas talk to one another during timing tasks. It's really just a model of how the cortex, broadly defined, accomplishes timing. And it focuses on the cortex because it tries to take circuitry that we see in many cortical areas and use it to explain why we see something called ramping activity in so many different cortical areas during timing tasks. And to clarify what ramping activity is, I'll plot what we will call a purported ramping neuron, what it might look like during our task. We're presenting this tone that tells the animal to respond after 10 seconds here. And to clarify up front, like many grad students, due to COVID, I don't actually have any actual data as of yet with this task specifically. So all this is just, supported based on prior work, but this is what we would expect to see a neuron like this. So on the x-axis is time relative to this cue turning on, but now on the y-axis is the firing rate of this neuron. So at time 0, the tone pops up, and this neuron goes from a low firing rate to kind of starting to gradually increase its firing rate until it kind of caps out, or it can't physically fire faster than it currently is. And in my simulations, that's often 30 hertz, which is kind of arbitrary because the linear portion of this profile is the important thing. Because if we focus around the fact that right around our interval of interest, so 10 seconds, this neuron is typically firing at 15 hertz, we can conceive a way of how ramping might work, in terms of timing. If we imagine that this ramping neuron is, say, projecting to downstream motor neurons that can cause lever presses to be executed, they can time those actions effectively by just waiting for this ramping neuron to hit 15 hertz. Since that typically coincides with 10 seconds, those actions will be well timed. And within this kind of a framework, we can time any interval we'd like. So for example, if we were to present this light that tells the animal to respond after 30 seconds, all this neuron has to do is kind of decrease its slope. So slow down a bit to where it's going to hit this 15 hertz mark around 30 seconds now. And this is something that we do see in vivo during experiments, the scaling effect. So hopefully you can kind of get a sense of why we think averaging should work in the model, because you might imagine that if we represent both cues at the same time here, maybe the ramping neuron takes an intermediate rate between the two and it hits this threshold in between the component intervals. So that's, easy to say, but getting the model to actually do this is the hard part. So that's what we'll talk about next, and because it currently doesn't predict this. But one thing I feel obligated to shout out is that people who work with this task extensively are probably mad at me right now for not plotting 2 decision thresholds, one that controls when the animal starts and stops responding, so that burst. I'm going to stick with 1 threshold just to keep things accessible, but also because the graphs are about to get very dense. But I do hear you. So, so currently, the model doesn't predict this intermediate ramp. And to explain why, we have to get into how we simulate ramping neurons with the model, because we actually simulate multiple cortical populations that talk to one another and end up generating ramping activity. So this can get hairy, but fortunately we can stick to the highlights and simplify a bit, and it's really not that hard to understand. There are really just 2 types of neurons in the simulations to go over, and the first are called tonic neurons. So as the name implies, when cues are being presented during these tasks, these neurons don't gradually ramp up in their activity. They basically just start firing at some high rate and remain there. And I can plot what one might look like up here on the right. So when the tone is presented at time 0, this neuron transitions from firing at a low rate to essentially firing as fast as it can. Again, that's 30 hertz in my simulations. So not our ramping neurons, but they do help generate ramping activity by projecting to our ramping neurons, which I'll diagram down here. And an important property to emphasize about ramping neurons in the model is indicated by this loop-to-loop in this neuron's axon. And this indicates self-excitation. So there's recurrent excitation in these neurons. And what that'll do is if a tonic neuron delivers a spike onto a ramping neuron, the ramping neuron is going to fire and send output to downstream motor areas, but it'll also wrap back onto itself and self-excite. And even if the ramping neuron doesn't get further external input, that self-excitation alone can cause the ramping neuron to fire again. And you'll get more self-excitation, more firing. So basically, a single spike from a tonic neuron will cause the ramping neuron to engage this positive feedback loop where it's in this depolarized state and causing itself to fire. And if it's in that depolarized state and a tonic neuron delivers another spike, it'll just bump up the firing rate a little bit more. And if it gets another spike, it'll fire a little bit more, et cetera, et cetera. So the idea is that if we feed the ramping neuron consistent spikes across time, we'll consistently bump up the activity of the ramping neuron, and we will get a linear profile out of it. And the way to tune the slope in this model is to adjust the number of tonic neurons that become active when a given cue is presented. So when the tone is presented, we need a steep slope out of the ramping neurons. We'll turn on all three here that are diagrammed. But in contrast, if the light is presented, we need to decrease the slope. So we might just activate one. So we feed the ramping neuron less, activity per unit time, so less bumps, and we'll get a shallower slope and hit that threshold around 30 seconds. Now, ideally, in the current form of the model, what we want to see is if we represent both cues at the same time here during a temporal averaging experiment, according to these diagrams at least, we would want only 2 tonic neurons to become active because we need all 3 to get that steep slope when the tone is presented, and we need just 1 to get that shallow slope when the light is presented. So to get an intermediate slope, we need 2 to become active. And currently the model doesn't predict this. And to explain why, we just have to go up one more layer and kind of clarify this magic that's going on up above these tonic neurons. So currently I'm just, presenting a light icon or a tone icon, and they're magically activating the appropriate tonic neurons for that cue. But in reality, in the simulations, what we do is we simulate sensory responsive neurons that kind of activate for a bit whenever a cue is presented. So for example, when the tone is presented, this neuron becomes active and it's linked up with the appropriate tonic neurons for that cue. So all 3. And in contrast, when that light is presented, this neuron becomes active and it activates just 1. So we'll get that shallow slope. So this is all we need to explain why the model doesn't account for averaging, and kind of tying everything together here with these graphs. Present the tone, we get 3 tonic active neurons active. So we'll get a steep slope out of a ramping neuron, and now simulating behavior in the model, we'll get responding around 10 seconds. In contrast, when we present the light, this neuron activates 1 tonic neuron, we'll get a shallow slope and responding over 30 seconds. Now, importantly, according to this model, if we present both cues at the same time, this neuron will activate all 3 tonic neurons, and this one will send redundant excitation to this 1 tonic neuron. And importantly, as I said before, tonic neurons are already thought to be firing as fast as they can, so that redundant excitation isn't going to do anything. We're just going to have 3 active tonic neurons, so stuff will match what we see during these tone trials. We'll get a steep slope out of the ramp and responding over 10 seconds. So that's the current problem, but there is a simple way to modify this circuit to get it to produce averaging. And it's kind of intuitive. So it relates to what's going on with these sensory neurons up here. In the current version of the model, when these cues are presented, these neurons send excitation to the appropriate cues or tonic neurons needed for that cue. In my version, the modification I'm proposing here, they still do that, but they also send inhibition to the tonic neurons that the cue does not need to time that interval. So we can visualize this here for the light. So when the light is presented, this neuron becomes active, excites this one still, but now it's going to inhibit these 2. And things to clarify, it might seem strange that a neuron has both an excitatory and an inhibitory projection at the same time. This is just a heuristic diagram. So in a fuller one, I would include an excitatory projection onto an inhibitory neuron that in turn inhibits these tonic neurons. But I'm trying to keep it simple. And relatedly, there's nothing to plot in terms of the tone here because it's already using all 3 of the diagram neurons. But importantly, this will yield averaging, and I can explain that as follows. So nothing's really going to change here in terms of what happens when we present these cues individually. When we present the tone, it's still going to excite these 3. When we present the light, it's still going to turn on this one, but now it's going to guarantee these 2 remain off by inhibiting it. But that inhibition doesn't really do anything when you have a single source of information. It's really built for these weird situations where you have to juggle two things at once, like during these compound trials. Because during a compound trial in this model, this tone neuron will try to excite all three tonic neurons, but now this light neuron will send still redundant excitation to this one tonic neuron, so this one's guaranteed to be off, but things are more uncertain for these remaining two, because they're now getting competing excitation and inhibition. And if this is, balanced, whether or not these tonic neurons become active during a trial is going to be like flipping a coin. During half the trials, the excitation will win, the neuron will turn on. During the other half, the inhibition will win, and it'll remain off. So we have, in other words, an activation probability of 0.5, and these two tonic neurons are getting the competition. So on average, one should turn on during a trial, and the other should remain off. So along with this one, we'll have on average 2 active tonic neurons. So we're going to get an intermediate slope, and we are going to get temporal averaging behavior, which is great. I can't believe there was a solution that simple this whole time, at least one. So I've gone over time a little bit, and I'm sorry for that. So I'll fly through this. Future directions, some work that I've done with Matthew Mattel has suggested that temporal averaging conforms to Bayesian models of decision-making. Rats oftentimes weighted averages rather than, arithmetic ones or harmonic ones or whatever. So when you're doing math with a Bayesian model, you're doing, equations for probability density functions and et cetera, and it's kind of abstract. So it'll be interesting to see how that maps onto this circuit, because you can weight different cues by, increasing their excitatory or inhibitory weights, respectively for the tone and light. And following from that, recent data from Fuat Bolchi's lab suggests that mice actually average number during counting tasks. And while making this talk, I actually realized it wouldn't be difficult to turn this into a counting circuit if you just include a global inhibitory neuron that links up, or these tonic neurons link up to. This will cause the tonic neurons to burst rather than fire tonically, so the ramping neuron will kind of count in quantal increments. So, if that works, all of this stuff will come for free in terms of the counting tasks. And finally, I've kind of, hit the highlights of temporal averaging. Behavioral data is a bit more complex than what I presented here. There are many cases where we see really robust temporal averaging that's generally scalar, but there are a lot of weird situations where the rats do strange things that we currently can't explain. We see kind of averaging-ish behavior. And while I haven't had enough time to explore it, the model also does strange things in certain cases. So I want to see if that weirdness of the model might map on to the weirdness of the behavior, because we currently have no idea what's going on in those idiosyncratic situations. But for now, I just want to say thanks to you all, everybody in the Freeman and Parker labs, everyone in the Mattel lab, and Matthew Mattel. I'm very lucky to have been able to work with him, my funding sources, and also, of course, the rats. So I can take your questions now.
Or Tanya?
Sure. Hi, Ben. That was really interesting. I was wondering if you had looked into it all, how the behavior and then the, by consequence, the ramping activity in the cortex looks when the intervals are trained on 2 separate responses, even when the cues are concurrent. I was wondering how that plays out, because I've looked at, obviously I've seen research where the cues there's 2 separate cues on 2 separate responses, but I was wondering how it manifests when the cues are concurrent, and if you've looked into that at all.
Yeah. So in terms, actually the first manuscript I ever published was an experiment where we associate each cue with a distinct response location. The left node spoke for tone, right node spoke for light. In terms of the behavior, when we present both cues, you'll still see, it kind of looks like a generalization thing, where during most trials, the animals will respond generally on the long nose spoke, because that's where the peak time falls closer to during those trials. So it's still like averaging behavior. There will be a proportion of trials, around 10%, where they respond on the short nose spoke, but those responses will also be shifted rightward. So it looks a lot like Verot's law or migration effect, basically, which is pretty cool. So there's a paper there. In terms of what would happen for the ramping activity, I have to turn this more into, so there would be 2 components to like build into the circuit. One that controls where the animal responds, and then the other that produces averaging. I don't know. I'd have to think about it more. But if you built both into the same timing circuit to relate when the ramping neuron is going to hit the threshold, late or early, to map on to where they respond, you could probably do it. It would get more complicated though. So it's a good question.
Yeah. Thank you.
No problem.
Okay, Shannon, maybe we could give it another try.
Yeah.
Yes, sorry.
So I don't know if you answered this when my computer was frozen, but I was wondering if it made a difference whether the sound and light stimulus were switched, if the neurons are entrained differently because it's an auditory modality or because it's a light modality, and if you would see a difference in that averaging.
Yes, yeah, you actually do. I'm interested to see why you asked that question. But yeah, so this is kind of one of those weird situations that I was talking about. So if the tone is associated with the short interval and the light with the long, you see averaging. And it's always there. But in the reverse situation where the light is short and the tone is long, the animals seem to, at least there are different explanations, but what they seem to do is time the light in a normal manner during some trials and also average during others. So they kind of switch between the two. And yeah, why is really difficult. And I kind of wanted to get points on the board and just explain basic averaging. Getting to this weirdness is going to be difficult. It seems to be inherent differences in how rats ascribe value to cues that are associated with appetitive rewards. So like sugar or food. They seem to be biased to associating lights with appetitive rewards more readily than tones. And you see the reverse if we're using a negative stimulus, like a shock or something like that. If there's a negative valence, they'll associate it more with the tone than the light. So I wish we had another modality to work with because it would be nice. But yeah, that's an open question. Yeah.
Yeah, that's really interesting. Thank you.
No problem.
Okay, we have Patrick Simon.
Hey, Pat.
Hi, Ben. That was beautiful. I was just wondering what some of the funny things that the model predicted were, because those would be really good predictions to test with an experiment.
Yes, they would. Yeah, like I said, I had time to work on this in the pandemic, and I got it to the point where it worked, and then research started up, so I got slammed again now. But basically, well, I haven't explored it enough. It kind of looks like this modality effect, this distribution that you see here. If you start shifting the excitatory inhibitory balance, if you think of it like a single distribution on an activation function for the tonic neuron, if you get it toward the tails, you'll start to see this binary switching where the whole population times the short interval, and then in other trials it acts more probabilistically if it falls in the linear region. So you'll see kind of an averaging like behavior thing. It's not exactly like the behavioral data, but it does get to it a little bit. Make sense?
Yeah.
Okay, cool.
Okay, there are two more questions and then we should move on. So Martin Wiener.
Hey, Ben. Great talk. Really liked it.
Thank you.
I was also glad that you mentioned the tone short, light long stuff, because that was going to be my question for you. But one thing I'm curious about is, I don't know if anyone's done this with animals or humans, but has anyone looked at averaging using empty intervals that have been cued with one modality versus another? Because, humans can time, and animals can time, the gap between two stimuli. And there does seem to be some effect of whether the stimuli are cued by auditory or visual, pings. And I'm wondering if anyone's done it, if there was a compound cue presented at the start that leads to some kind of averaging behavior, and if the model that you have requires sustained sensory activity in order to generate these responses.
So to the latter question, no, it doesn't require sustained presence of a stimulus. At least in my version, the cues elicit transient responses. So it's like a transition triggers these neurons. In terms of whether or not people have done empty intervals, no. And I've also wanted to see that experiment. So yeah, it would be an awesome, I guess that is like a new modality in a way. So yeah, that would be a good experiment to run. for sure, you should do it.
Cool.
Or I should.
One of us should.
Okay, and the last question is from Peter Balsam. So Peter, go ahead.
Hey, Ben. Hi, everybody. Great job, Ben. Really nice talk. I guess I was thinking about what naturalistic behavior might be. And sometimes when you get ambiguous information, you might respond to the average. But I think a lot of the time, what people and animals might do is try out the old things first. So try one thing, then try another thing, and then move into averaging maybe sometimes, but sometimes just stick with the old ones. I was just wondering what your thoughts were about when those two different strategies might apply, and if there's any evidence in the data very early on that maybe they are trying one thing or the other thing and then flip to the averaging strategy.
Yeah, so I do think there's like a bit of variability across trials in terms of what the animals actually do. And that was like one of the important things about that dual nose poke design for the two cues. You can kind of start to see that a little bit. It's very difficult to kind of distinguish with just a single response manipulandum. But yes, I would expect there to be transitions in variability in the strategies the rats employ. It's just that picking, like how to quantify the behavior in a way that doesn't make things ambiguous is the tricky part.
Yeah.
In my view. Yeah.
Thanks.
Well,
Okay, all right. Thank you so much, Ben.
Okay, hi everyone. Thanks so much for having me today. So as Bashak was saying, I work with Dr. Wilson Joyner, and today I'll be presenting a collaborative project that we have ongoing with Martin Wiener at George Mason University. And I'll start out with some background. As many of us probably know, time perception is variable, and this can depend on the sensory properties of a timed event. One account that kind of tried to integrate findings across studies by Matthew and Meck introduced the processing principle, where the duration of an event is positively associated with the vividness of a percept. And actually no such account exists for motor properties influencing timed events. And this is really relevant because sensory events don't just happen in a vacuum. We continuously interact with our world. And in fact, much of our motor plans are guided by a particular goal that will elicit a particular sensory response. This has been investigated tied to movement parameters such as speed and direction. And I'll also show previous work from Dr. Wiener and Dr. Joyner that showed that concurrent movement can actually improve time perception. So in this task, participants were seated at a robotic arm manipulandum, and they grasped the right handle, and this could move freely along a planar workspace. They needed to hear a range of tones between 1 and 4,000 milliseconds and indicate whether that tone was short or long compared to all tones heard so far. They were also assigned into two groups. One group was allowed to move throughout the tone, and the other group was held in place at the start location until tone offset, and then they were allowed to respond. Here are the results from that study, which showed that people in the free movement group had a steeper psychometric function, indicating they had greater perceptual sensitivity than the people in the hold group. We're actually building on this study in the work I'm presenting now. And here is a quick video illustration of how a trial would have gone. So they are hearing the tone, and then they are deciding eventually to select the short response. We're using this same paradigm in the current study, except that all participants move on every trial. The new manipulation we're introducing here is applying a random viscosity level on each trial. So they'll encounter some resistance on the handle, making it more difficult to move. Viscosity 0 can be thought of as the viscosity at which it takes barely any effort to move the handle, whereas 36, you can imagine stirring a pot of molasses. So there's quite a bit of resistance there, and then we have these intermediate values. In the first experiment, we tested this in a temporal bisection or temporal discrimination procedure. And in experiment 2, we tested this in a temporal reproduction procedure. We also employed computational models to describe these behavioral results. In particular, we wanted to dissociate the perceptual effects from the downstream effects in both of these. I will explain both of these in a moment. A trial would go as follows in the temporal bisection procedure. They would be locked in place in the start location in the center there. During a warm-up phase, the handle would be released, or the lock would be taken off, and movement would be allowed. Then, while movement was allowed, an auditory tone would play, and after the tone elapsed, they would need to indicate whether it was short or long. And I will note that the target assignments were switched between participants, so they were randomly assigned to short being on the left or to the right. Here are the results from that temporal bisection experiment. On the left, we have a representative subject psychometric functions separated by viscosity. And you can see that there tended to be a linear shift of the bisection point to the right, which indicated that overall there was a greater proportion of tones being categorized as short. We extracted these 4 bisection points for every participant, and in the middle you can see that we fitted regression slopes to each participant's 4 viscosity bisection points. And then on the right you can see that we plotted every participant along this distribution to show kind of where it would cluster, and the slopes were significantly above 0. So this indicated that overall there was this effect where encountering viscosity or some degree of resistance during a trial biased perception such that intervals were perceived as shorter. We also applied a hierarchical drift diffusion model, and I'm sure many of you are familiar with this, but I'll quickly explain what these parameters are. Each trial can be conceptualized as a drift process between 2 response boundaries. So this is a 2 alternative force choice task, and there is a long boundary and a short boundary. And the drift process approaches one of these boundaries, and once it hits the boundary, then the decision is made. The drift rate, or basically the speed with which it approaches one of these boundaries, indicates basically the rate of evidence accumulation. The threshold describes the width of these decision boundaries. So as you can imagine, you can make these boundaries wider, which would kind of indicate that the criterion is more conservative. So it would take longer to hit the boundary, but on average, they would be more accurate. The starting point, Z, is exactly that. It describes where the drift process begins, and when there is some kind of decision bias, this is off-center. So in that case, it would take less evidence to elicit one response over another. There is also non-decision time, which describes the most basic perceptual and motor processes that have nothing to do with the decision process. Here is what we found for those results. So we saw that there were significant effects of viscosity on drift rate and threshold and bias. The top row here shows viscosity on the x-axis plotted against these parameters. And we were particularly interested in the drift rate. It tended to shift from the long boundary towards the short boundary. So you can see it's kind of near 0, and then it goes below 0. We thought this was interesting. So we thought this might have some kind of correlation to the rightward shift in the bisection points that I just showed you. So for each participant, we took their bisection point slope that I showed, and we took their drift rate slope here, and we plotted them against each other on the bottom row and found that there was a significant negative correlation, which is evidence that these effects of viscosity are occurring at a lower perceptual level, so through the drift rate. We didn't find any correlation with the bisection point shift and these other parameters. But we wanted to kind of confirm these results with an alternative paradigm. So here we tested people on temporal reproduction, and it was very similar in that people were moving while they were timing intervals, but there were just a few key differences, which I'll go over. Each trial started with the robotic arm in one of these randomized locations, and this was kind of an extra layer of precaution to make sure that people weren't using the same stereotype trajectories or using some kind of heuristic for timing. And then movement was cued, and then once the person started moving, the auditory tone would come on, and they needed to sustain movement until the end of the interval. So this is slightly different from the first experiment because we actually required people to move here. And then during the reproduction phase, the robotic arm brought them back to the center, and they reproduced the duration with a button press, with a button attached to the handle. Here are the results for the temporal reproduction experiment. The viscosity tended to bias intervals to be perceived as shorter. So if you look at these reproduction slopes, intervals were generally overestimated, but the degree of estimation decreased with viscosity. So we examined this effect for each participant. So in the center, we have a slope for each participant describing the tendency to underestimate. So offset here on the y-axis is just the produced interval minus the true interval. And so overall, people tended to show a negative slope here, and in the distribution on the right, they were significantly below 0. We also applied a Bayesian observer model by Remington and colleagues. And in this process, an interval timing process is conceptualized as encountering a duration out of some range of durations that you're being tested on. And you have a measurement process. Of course, this measurement process can't be perfect, so there's a degree of noise associated with it. And sometimes this measurement distribution here isn't centered on the true duration, but there is some offset bias that's consistent. This is combined with the prior distribution, or what they call the temporal context. So this is just the knowledge of the range of durations that you've become accustomed with. And then you produce the interval with some degree of production noise, because again, we're not perfect, there will be some noise. Here's what we found from this model. If I could direct your attention to B, again on the top row, we have viscosity on the x-axis and the parameter estimates on the y-axis. So we found significant results in production noise and in offset as a function of viscosity. And we more closely examined the offset parameter here. We went ahead and plotted the tendency of viscosity to decrease interval estimates, as I showed with the reproduction slopes. And here, for each participant, we plotted that slope against this offset downward slope here. And there was a strong positive correlation between these, suggesting that the observed results were the observed results with the reproduction slopes were from this offset parameter. Again, kind of converging on the result that viscosity shortens time perception, and this is occurring at a perceptual level versus a downstream decision or production level. So here, I'll just go over some main points. This basically showed that restricting movement during interval timing led to a compression of time intervals. And the kind of important addition to the current body of work was that we externally modulated the type of movement that people were allowed to do. Whereas in previous studies, they did examine movement parameters such as speed, but it was because they told the participant to move fast on some trials or slow on some trials. And the computational models we employed suggested that these changes were occurring at the perceptual level. And some questions for future work or some food for thought are, when are movements beneficial versus when do they bias timing? So in the previous study I cited, Wiener et al. 2019, they showed that movement somehow improved time perception without biasing it versus the non-movement conditions. And across a lot of different studies, movement shows biasing effects. So further investigation is needed to kind of dissociate those mechanisms. And also, which effects are modality specific versus supermodal? So are these manipulations affecting timing in earlier sensory regions, or are they targeting higher core timing circuits? And finally, can this information be used in clinical applications for disorders with parallel motor and timing deficits? So I'd just like to thank the Joyner Lab and the Wiener Lab, and for the awesome mentorship I received from those two, and the people in my lab who helped me learn MATLAB and do a lot of these analyses. I'd also like to thank my graduate group and the funding source. And if I don't have time to get to all the questions, my email is posted here as well. Thank you.
Thank you so much, Rose. This was incredible. It sounds like really fun to do these types of projects, I guess.
Fun.
So yeah, so yeah, we do have a couple of minutes for questions. So I see Peter unmuting himself. So if you do want to ask a question, Peter, go ahead. Yeah.
Oh yeah, great talk, Rose. Really nice,
Thanks.
really clear. I was wondering, something that also changes when you change the viscosity is the actual movement time itself. Have you looked to see whether that might be possibly influencing the judgments also?
The movement duration, or?
Yeah.
I think that what was actually affected, and maybe I'm misunderstanding the question, I think the movement durations were very similar because they began once they saw the warm-up phase, and then they continued all the way until a choice was selected. And I think the main movement parameters affected here were the speed of movement. So so when there was higher viscosity, the movement length was overall shorter, and people tended to compensate a little bit by pushing harder. But overall, yeah, I think that was what was mostly affected.
Yeah, that's great.
Okay, Pat, go ahead.
That was very nice, Rose. I wonder if what happens when the viscosity goes up, you're pushing harder, so you're getting more somatosensory, maybe you're getting more somatosensory feedback. And so, like thinking about like Ben's model, for example, maybe what's happening is you're driving the drift process just a little bit harder because you've got more activation in somatosensory cortex. And I wondered if you could, if that's on your radar as far as something you could test with, I don't know, fMRI or something like that.
Trying to think of how I would do that.
well, for example, you could, you know, have a low viscosity condition that you compare with a high viscosity condition. And well, I mean, you should just see more activation in somatosensory cortex than I would guess in the higher viscosity, but I don't even know if that's true.
Yeah, I wonder if there would be kind of like some kind of tonic activity that would somehow affect the drift process. Kind of trying to think of Ben's model, but I'll have to think more about that.
Okay.
Okay, I think that's it. So thank you all for joining us today, and thank you, Ben and Rose. This was really great. So so this was the second and the final journal club of this year. So the next virtual journal club will be in mid-late January, and it will be led by Patrick Simon. And he will actually hold a tutorial on the drift diffusion models. Once we finalize the details of that journal club, we will let you know. So happy holidays to everyone, and Happy New Year, and hope to see you all soon.